What's up, everybody? Welcome to a new lecture and welcome to Chapter 4. So Chapter 4 is all about orbital maneuvers, or in other words, changes to spacecraft current orbit to make it a new one. Okay, so what would be the situations where we would like to change the spacecraft orbit? Well, for example, if after launch, the spacecraft didn't end up in the appropriate orbit, then the spacecraft will need to make correction based on its own engines or thrusters to modify its orbit and make it what it really wanted to be. Another more contemporary situation where orbital maneuvers are often required is to dodge a space debris, right? The space station needs to perform corrective maneuvers once in a while to end up in a slightly different orbit, otherwise it would end up in a collision with a piece of debris. So two situations, for example, where orbital maneuvers are commonly performed. Also, when you talk about the final phases of a rendezvous and docking maneuver, say the Dragon capsule needs to dock with the station, then it needs to perform orbital maneuvers to make sure that its docking port is properly aligned with that of the station. Okay, so this is going to be the bulk of Chapter 4, and specifically we're going to take things here one step at a time. So the first kind of orbital maneuvers we will analyze are those that are said to be impulsive. So impulsive orbital maneuvers corresponds to those that happen instantaneously. Although in practice it's not possible to do orbital maneuvers in such a rapid time frame, but nevertheless, for analysis purposes, this is what we're going to assume. So again, impulsive maneuvers will change the velocity of the spacecraft instantaneously without changing its position. What I mean by that is the following. So if the spacecraft is coasting along its orbit and at some position decides to do an orbital maneuver or firing thruster maneuver, then what's going to happen is that instantaneously the spacecraft would go from its current velocity to, say, its new velocity, v2. Okay, so v1 is prior to perform the orbital maneuver, v2 is immediately after, such that the change in velocity vector from its initial velocity up to its final velocity will be denoted by delta v vector. And notice that within the impulsive orbital maneuver assumption, the change in velocity vector happened over the same orbital position vector. Okay, so spacecraft was at r vector traveling with v1, and boom, all of a sudden its velocity jumped to v2 at the same position vector. This is the impulsive maneuver assumption with which we're going to begin this chapter. This delta v here is a change in velocity, as I said, and in that case I would just be v2 minus v1, or the initial velocity plus the change in velocity gives us the final velocity vector v2. And this is the impulsive orbital maneuver, or in other words, the impulsive thruster firing. Now, you may think, well, wait a minute, in practice, as you said, it is impossible to do an impulsive maneuver. Correct, but still this assumption holds well, because if you think about the action of opening a thruster for X number of minutes to boost the velocity of the spacecraft and then shutting the engines off, then that entire period where the thrusters were open correspond to a few minutes at most, okay? And then if you compare the amount of time that the thrusters were open in minutes compared to one orbital period, which in LEO we think about an hour and a half for one orbit, then that short amount of time over which the orbital maneuver are performed in practice compared to one orbital period, that time is quite small, and this is why the impulsive assumption holds well in practice. Okay. Now, related to the change in velocity vector caused by the impulsive orbital maneuver is the magnitude or the norm of this vector that we shall denote delta V. Okay? Delta V vector is this, and the norm of this vector is the scalar quantity. Now, one thing to note here, and make sure that you follow closely what I'm going to say, or listen closely, is that because delta V, through its very definition, is a norm of a vector, or the length, it has no choice but to be positive. Okay, so delta V magnitude is always a positive scalar. Delta V magnitude is always a positive scalar. Delta V magnitude is always positive. Okay, make sure you never forget about that. And this is due to the fact that this is the norm or the length of a vector. Okay, so this quantity here will always be greater than 0 regardless of the fact, if we reduce or increase the current spacecraft velocity vector in terms of its magnitude. Okay, because here, as you could see, I increased the velocity vector from V1 to V2 because V2 is longer than V1, but another situation could have been V1 like this and V2 a smaller one, smaller V2 vector, yet the delta V in terms of magnitude, even in that case where the velocity vector got decreased by a retropropulsive maneuver, or in other words, you are decelerating, will always be positive no matter what, okay? Because this does not contain any information about the direction of the actual maneuver. If it is in the same direction as the current velocity or in the opposite direction to slow the spacecraft down, that quantity here does not care about the direction, okay? It's only the norm of the actual delta V maneuver. Okay. And turns out that this parameter, delta V magnitude, that I shall denote as just, or refer to as just delta V from there on, is closely related to the amount of fuel needed to perform that specific orbital maneuver. So the way we quantify fuel usage required to perform an orbital maneuver is through the Tchaikovsky rocket equation, okay? Let me spell his name properly. Tchaikovsky rocket equation. So that equation relates the delta V in terms of magnitude of this orbital maneuver that has both direction and magnitude here. So just the magnitude is actually equal to minus G naught, where G naught is the gravitational acceleration at sea level, okay, times the ISP, which is the specific impulse of the fuel being used to perform the maneuver. Is it a coal gas engine? Is it a liquid propellant? Is it a hybrid rocket? So all those different technologies that are used to perform an orbital maneuver will have different ISP values, okay? And those ISP have units of seconds. So this is the specific impulse, which is related to the rocket technology being employed to do the maneuver. Okay? That was sea level gravitational acceleration, obviously. And those two terms are being multiplied with the natural logarithmic of the ratio between m and m naught, where m naught was a total mass of the spacecraft prior to the burn or the maneuver, and m is the mass of the spacecraft after the burn or the maneuver. And the reason why those two masses are different is because if you want to perform an orbital maneuver, it means that you need to use fuel, which is stored in some storage tank inside the propulsion system of the spacecraft, okay? Because you don't have an unlimited amount of fuel, obviously, on board. So every time you perform one orbital maneuver, the fuel left is less than before, okay? So this number will always be smaller than this one. So final mass after the maneuver, and then the mass right before performing the maneuver. So this is a Tarkovsky rocket equation that is used to quantify the amount of fuel required to perform a given delta V maneuver. Although in this form it is not the most useful equation we're going to play with, so what we can do is turn this equation upside down and then have delta M on the left-hand side of this equation. I'm going to say delta M, where delta M is initial mass minus the final mass. Or in other words, the fuel mass required for the maneuver is going to be equal to the initial mass of the spacecraft times 1 minus exponential of minus delta V over G naught ISP. Okay? So based on the analysis we're going to do in the subsequent subsections, we're going to come up with different ways to calculate our delta V in terms of magnitude of a change in velocity vector, and then knowing the initial mass of our spacecraft, the technology we're going to use to do the delta V maneuver and G naught, which is constant, then we'll be able to figure out how much fuel mass we need to carry on board to perform that single maneuver, which is quantified through the delta V. Now, one spacecraft mission typically involves quite a bit more than one orbital maneuver. So what in practice people do is that they calculate the individual delta V's and then the individual delta M's, and then sum up all the delta M to come up with the final fuel budget of the entire spacecraft mission and size the engine accordingly. But because to size or to determine the fuel mass needed to do all the delta V's for a given mission, we need to know the initial mass of the spacecraft, which includes the propellant being carried and the rocket technology on board. This is kind of a circle problem, because to know the amount of fuel you need to expel to do a delta V maneuver, you need to know the amount of fuel you had before, because this is part of M naught. So as you will learn in Aero 4442, spacecraft propulsion, there are ways that we can solve this problem, but here in this context of this course, M naught will always be given to you as a number, and then it's going to be up to you to calculate delta V based on different type of analysis, and then just calculate the fuel needed to do that single orbital maneuver. Okay? So this is kind of the introduction to orbital maneuvers. And again, as I told you earlier, we're going to begin very slowly with very simple maneuvers, and near the end, look at more complex maneuvers. But the first kind of maneuver we'll be looking at in 4.1 is a single impulsive coplanar maneuver. Okay? So single meaning that only one burn or orbital maneuver will be considered in this subsection, because ultimately we'll be looking at double impulsive orbital maneuvers, where to go from one orbit to another one, we'll need to apply two burns at different points, and so on and so on. But here, to begin with, one maneuver will be sufficient to transfer the spacecraft from its current orbit up to the final or desired orbit. Impulsive meaning that the change in velocity vector will happen instantaneously, like that. So without changing the current position vector, we're going to see that the velocity will jump from one to another one. Coplanar maneuvers will mean that we're not going to change the orientation yet of the orbital plane. Okay? So if this is M1 and you have the spacecraft original or current orbit like that, what's going to happen if we talk about coplanar maneuvers is that everything will be taking place in the orbital plane, which is the plane of the whiteboard here. And therefore, we're going to go from a position vector r with the spacecraft current velocity vector v1 up to another velocity vector at the same position, but everything will be contained within the board, within the whiteboard plane or the orbital plane, such that that would mean that the orbit here could be looking, oh boy, it doesn't look very realistic, but essentially we'll be rotating the orbit within the orbital plane, or stretching the orbit and changing its semi-major axis, and therefore changing its eccentricity as well. Okay, so single impulsive coplanar maneuvers will only change semi-major axis, eccentricity, and or argument of perigee omega. All right? So the impulsive assumption means, what did I want to say here? Yeah, because of the impulsive assumption, it means that the initial orbit and the final orbit have to intersect at one point, because they are going to share the same position vector at that point, yet having two different velocities, okay? So I shouldn't have erased that, but if you have one arc of an orbit and another arc, and this is the final orbit, orbit number 2, and orbit number 1 here, as you can see, they need to intersect at one point such that the position vector is the same for both orbits, yet having two different velocity vectors like that. So this is the implication of using the impulsive assumption here, is that both orbits need to intersect at one point. Okay. So not only we're going to use single impulsive coplanar maneuvers, but also I'm going to say plus another assumption, which is tangential to begin with, okay? That assumption will also get relaxed down the road, but to begin with, only tangential maneuvers will be looked at, i.e., we're going to look at maneuvers that will only stretch or compress the velocity vector without changing its direction, okay? Meaning that we need to find a location along the current orbit and the final one where both orbits intersect, obviously, because of the impulsive assumption, but tangential meaning that we're not going to change the direction of our current velocity vector. Turns out that along an elliptical orbit, there are only 2 points then that we can apply maneuvers if we want to consider all those assumptions, because both orbits need to intersect and they need to share the same direction of their velocity vectors. Turns out that, again, along the elliptical orbit, only the perigee and the apogee are valid locations then to apply a delta V maneuver. Because at that point here, you can go from one orbit to another one without changing the position vector. That's the impulsive assumption. And because of the tangential assumption in coplanar, it means that only at that point both velocity vectors are allowed to be aligned collinearly, okay? So only at the perigee and or at the apogee. If you were to do a maneuver at the apogee instead, you could go from here, do a retro burn, and lower the perigee distance like that, for example, okay? So there are a lot of assumptions, I know, to begin with, but again, they're going to be relaxed later on. So let's start easy, and then let's get comfortable with this concept of changing the velocity vector on the fly, and then we'll see what we can do with that in terms of practical applications. Now, the first single impulsive coplanar tangential maneuver is going to be in 4.1.1, circular to elliptical. So meaning that the initial orbit in red is a circular orbit around M1. But damn, that's not what we wanted. The launch vehicle screwed up and put us into a circular orbit. That's not good, because what we really wanted in terms of orbit was to have an elliptical orbit. Well, all you have to do, because the radius is constant at any point along this orbit, is to thrust at any point. I'm going to pick this one here. Apply a delta V maneuver such that this point now becomes the intersection of the initial and the final orbit, and kick us into an elliptical orbit, which would look like this. Okay? So red is the initial circular orbit. We picked a point along this circular orbit, increased our velocity vector, or increased the speed. So we went from v1 vector to all of a sudden v2 vector at the same point without changing the position vector, like that. And therefore we have increased the net orbital energy by applying a propulsive maneuver in this direction. Note that we didn't change the orientation of our velocity vector. This is a tangential assumption. And then as a result, we end up in an elliptical orbit like this, such that if you go from a low circular orbit to a high elliptical orbit, it means that the point of application of your orbital maneuver then becomes the perigee of the final orbit, or the perigee of the elliptical orbit, okay? Such that if we want delta V in terms of scalar, which is the length of this particular vector, right? Delta V vector would be the difference between V2 vector, which is larger than V1 vector, V1. So like this. Then this again needs to be positive. So when we're going to look at delta V in terms of scalar, then we have to make sure that we do the subtraction in a proper order. Because if you want to calculate delta V and you were to take the speed that the spacecraft had at this point along the red orbit, which is V1, minus V2, then you would obviously get a negative delta V, and I would remove 50% of the final mark for that question, because delta V negative is just impossible. Okay, so think about it. Don't forget about this concept of performing the subtraction in the correct order. I know it looks trivial and obvious, but I guarantee that close to 50% of you will do that mistake on an exam. Okay, so delta V magnitude is going to be then speed 2, which is the largest, minus speed 1. Now, how can we figure out the speed number 2, or the speed that the spacecraft has at this exact position, but along the green orbit, which is the higher energy orbit, the large elliptical orbit? Well, all we have to do is to apply this Viva equation at the perigee of the elliptical orbit, which is going to be square root of mu times 2 over r minus 1 over a. Remember, this is vis viva. I'll just apply this viva equation along the elliptical orbit at a very specific point, which is the point of application of the orbital maneuver, such that here, instead of just letting r being a generic r, I'm going to specify that this is rp, because this is the perigee. Okay? And A here refers to the semi-major axis of the big elliptical orbit, and minus V1, which is the speed that the spacecraft had along the initial orbit. All right, initial and final. So the initial orbit being a circular one, there is no perigee, there's no apogee to consider. So all we have to do is take the square root of mu over r, and that will give us the speed at any point along this circular orbit that has a radius equal to r. But here, just to be more accurate in the way I write things, I'm going to say that this is the radius of the circular orbit, and therefore name it rc. Okay? And if you do things in that specific order, you will for sure end up with a positive number, and that will make me happy when I mark your copy of the exam, and that will make you happy because you're going to get a good mark. Okay? So this is how you can then calculate the delta V in terms of norm related to this specific orbital maneuver that takes you from the initial circular orbit up to a big elliptical orbit. And that is by applying a maneuver in the same direction with which you were traveling at, okay? Which was upward like that. But what about the case where you're still circular to elliptical, but you want to do things the other way around? You'd like to get closer to M1. Well, let's have a look at this specific situation. Still within 4.1.1, circular to elliptical. Yet this time we will apply a retro burn, or in other words, we're gonna decelerate our spacecraft or decrease its velocity through the orbital maneuver. So let's go back to the drawing. Initial circular orbit, like this. With M1 right in the center. This is the Earth. And then you apply a maneuver. So again, pick a point. Any point is good along a circular orbit because the radius is the same and the speed is therefore the same throughout. So you are traveling with v1 in this direction, but then you apply a maneuver in the opposite direction, which slows you down and then decreases your orbital energy, and therefore you will end up in this kind of orbit, elliptical orbit with a lower amount of energy than what you had along the initial circular orbit. So this is orbit 2, which is your final orbit, whereas the red one was orbit number 1, which was the initial orbit. So then V2 is smaller at this point, which means that the burn must have been in this direction. Delta V vector is retrograde. Okay? And the job is always the same. So your task is to figure out delta V such that you can use the rocket equation, the second version, to figure out how much mass in terms of fuel the spacecraft would need to carry to change its orbit like that. So, in that case, remembering that delta V needs to be positive, are you going to take V1 minus V2 or V2 minus V1? Well, it seems like a trivial question, but again, I guarantee a lot of you won't do that properly in the exam. We're going to do V1 minus V2. And if you're not too sure about the length of the vectors to draw on your little diagram, just look at the shear size of both orbits to figure out which one would be fastest at a given point. And because the red one is larger than the final elliptical orbit, it means that inherently the spacecraft would have more energy along the initial orbit in that case, and therefore would travel faster even at the same position than it would along the small orbit that has inherently a lower amount of energy. Okay? So, how can we do this calculation? Well, it's same old, right? The speed along a circular orbit is going to be square root of mu over the radius of the circle, RC, minus the speed along the final elliptical orbit. This time, look at what we have. We are not anymore at the perigee of the ellipse, but we are now at the apogee of the elliptical orbit. So we better calculate the speed at the apogee of this particular orbit. So we're going to say square root of mu times 2 over r minus 1 over a. That's how I usually start writing the speed along the ellipse. And then I ask myself, okay, well, r, so what is this point in terms of application of the orbital maneuver? I go back to my diagram and I look, okay, so V2 is for the orbit in green. I had applied the maneuver at its apogee, so therefore I want the speed at the apogee for V2, which is RA, A for apogee, okay? And doing things this way will ensure that you end up with 100% for that question on a midterm, for example, or on a final exam, okay? So if you understood the concepts presented here, how to go from circular to ellipse in terms of small circular to big elliptical orbit, and do the other way around, going from big circle to small elliptical orbit, and just applying vis viva twice, right? This is vis viva applied for a circular orbit, essentially, because along a circular orbit, you would get mu times 2 over RC minus 1 over A. For a circle, A is equal to RC, so 2 over RC minus 1 over RC, and therefore end up with mu over RC. Well, if you understood the concepts here, you're good to go for the rest of this chapter. Okay, we're just going to keep playing with vis viva equations in a multitude of ways to address different situations, but that's going to be the bulk of it. All right? So now that we looked at circular to elliptical, impulsive, single impulsive coplanar tangential maneuver, that's a mouthful. We're going to look at the same thing, but then going from elliptical to circular. So now the elliptical orbit will become the initial orbit, and then the circular orbit will become our final orbit. But again, the concepts are exactly the same. I'm just doing all the different cases for completeness here. And also it gives you more time to kind of digest the information as I just do the same thing over and over again here, essentially. So elliptical to circular. So now the original orbit, and by the way, as you probably notice and as you will notice eventually in this chapter, is that I always draw my initial and my final orbit in terms of geometry and size and shape, roughly speaking, and I label the different variables that I need on my figures. So R, my V's, and so on, the direction of my delta V vector, so that when I come to calculate the delta V magnitude, I just go back to my illustration or figure, and it's really easy peasy for me to write the equation in proper order and figure things out. Because students will oftentimes just try to do things without the drawing or the illustration or the figure, and then get the order messed up, or for not only the order with which you subtract the different velocities, but also instead of going elliptical to circular, they would use the equation that brings us from circular to elliptical instead, and things like that. So really silly mistakes that can easily be avoided just by drawing a little illustration of the geometry of the initial orbit, the final orbit, and by labeling the different variables on that drawing, okay? So I know I want to go from elliptical to circular. So let's pick a random case where I go from, I'll always draw the initial in red, I believe. Okay? Arbitrarily, I'm going to start on a big elliptical orbit in red. That. And then with my M1. And then I'm going to pick a point of application, remembering that for tangential coplanar maneuvers, the point of application of my delta V has to be perigee or apogee, because we're not changing the direction of the velocity vector. And these are the 2 points of application that you can actually do that. So I'm going to go here. And then I'm going to kick myself into a lower circular orbit, like this. So just pretend that that is a circle. Not too bad on the screen, not too bad. So I was traveling with V1 at this point here, which is the perigee of the original ellipse. So is V1 larger than V2? What do you think? Well, yeah, because look at the size of V1, or the orbit number 1. So orbit number 1, which is the initial, is much larger than orbit number 2, and therefore the speed here, V1, has to be larger than the speed of orbit number 2 at the same point. Orbit 2, a small speed like that, and therefore delta V will be in the opposite direction like that, because I'm going from a high energy down to a low energy orbit, which means that I needed to slow myself down or apply a burn. If I'm traveling this way, the burn has to kick me backwards, okay? Like that. And the point of application is obviously at R vector like that, which just by inspecting the situation, I can easily tell that this is the perigee of the initial orbit. So, same as before, our job is to figure out delta V, which again is the magnitude of delta V vector, which will be equal to V1 minus V2 or V2 minus V1. Well, again, because I've drawn things before even thinking about equations, I can easily say that this is going to be V1 minus V2, just from the sheer size of both orbits involved in the process. Okay? Equal to V1. How can I figure out the speed along an elliptical orbit at any point? Well, applying this Viva equation, which is mu times 2 over r minus 1 over semi-major axis of said elliptical orbit. Now r, it's not some generic position at which I'm applying the burn, because the maneuver is applied specifically at the perigee, and therefore r becomes our perigee of the elliptical orbit minus the speed of orbit number 2, which is a circle, and you know that this is simply square root of mu over r, and because this is a circle, I'm going to write RC. But note that in that situation, in the previous one, RC is equal to RP because this is the same radius here, okay? Yet I like to denote those two differently because this is a circle and this is an ellipse at the perigee. But in terms of numbers, we're going to take the distance between M1 and the perigee for V1, and the distance between M1 and the circular orbit for V2, which happens to be exactly the same as RP, okay? But you already knew that. And that is going to give you delta V in terms of norm, which will be positive. Yes, good job. And obviously the other way around, going from a small elliptical up to a big circular orbit. Let me draw it, because otherwise I couldn't tell you how to derive the equation for delta V just based on what I just said. So I really need to see both orbits to easily figure out the order of the vectors involved and which one comes first and whatnot. So now this time we want small ellipse with M1 up to a big circle. Now, where would you like to apply the delta V maneuver in that case? Because if you apply the delta V maneuver here, you'll never be able to generate a circle bigger than this. Because if what you want is a circle and you apply the burn here, you are restricted to a circle that will be inside the ellipse, right? So if you want a bigger circle, it means that you need to apply the propulsive maneuver at the apogee and therefore end up with a bigger circle that has radius equal to the apogee distance of the initial orbit. Not too bad, not too bad. So this is orbit 2. This is the final orbit, and that was the orbit 1, the initial orbit. Here you had some velocity vector at the apogee, right? Because we decided to apply the burn at the apogee to increase the energy and therefore end up with a bigger circle, R. then the velocity along orbit 2 at the same point has to be larger. V2 like this, because we increase the energy of the initial orbit to be that of orbit 2, right? Such that delta V will be a propulsive maneuver increasing the net speed. It's in the same direction as V1, like that. And now, just based on doing a proper drawing, I have all the information I need to calculate delta V magnitude, which is going to be the larger speed, which is V2, minus the small one, V1, to really ensure that I end up with a positive number for delta V. What is V2? Well, this is the speed along a circular orbit, so square root of mu over RC, where RC denotes the radius of the circle, and minus the speed along V1 at what point? At its apogee. Because this is the farthest point from M1. We didn't apply the maneuver at the perigee this time, but at the apogee. So I'm going to apply this Viva equation to an elliptical orbit, like that, at the apogee specifically, and therefore I'm going to use the RA notation there. So you see, it is very simple. All you need to do is pay attention to what is given to you in terms of the problem and draw it, okay? I cannot emphasize that enough. If you don't draw the initial and the final orbit and don't label all the variables at play, you're going to get this wrong. Okay, so although the equations I'm giving you are in the lecture notes, you never have to go back to those to figure out, okay, circular to elliptical, that was section 4.1.1. Is it larger, bigger? Which one of these I use? No. Just do a quick hand sketch and do it on your own. Right? You're smart enough to do it without going back to the equations I'm giving you. So essentially, the way I end up with that, or the methodology, is a lot more important than the result, because the result you will be able to derive on your own. Okay? So that was elliptical to circular in both cases, where the initial is either smaller or larger than the final orbit. And obviously, the third situation in 4.1.3 is to go from elliptical to elliptical. Okay, so elliptical to elliptical. Let me draw an elliptical orbit as my initial orbit around M1. And then here I have two situations that can happen. I could go from this initial elliptical orbit down to a smaller elliptical orbit like that, or a bigger elliptical orbit like this by burning at the perigee of the initial one. Or I could apply the burn at the apogee and end up with a smaller elliptical like this, or also a bigger elliptical. So with elliptical to elliptical, you could choose the apogee or the perigee in terms of application of the orbital maneuver, and that will get you either a smaller or larger orbit. It just depends on the direction of the orbital maneuver. Is it retrograde, that slows you down, or in the same direction, pushing you forward or increasing the speed, okay? So here, arbitrarily, I'm just going to pick one case. So say I have a big initial elliptical orbit, M1, and let's pretend I applied the burn at the apogee here. So this is V1 along orbit 1, which is your initial orbit. And I want to go into a higher orbit, okay, much higher like this. Can you all see that? Yeah. Where essentially the apogee of the initial orbit becomes the perigee of the final one. That is an interesting situation. Okay. All the way like that. And in space, it makes that sound and that noise too, right? That's what it does, obviously. No, I'm kidding. Okay. So is V2 larger than V1 or smaller? Well, just look at the size and that gives you the answer. V2 is much larger than V1 because the orbit is much larger at the same orbital distance r, like that. And this is orbit 2. I don't know which case is presented in the lecture notes, but again, it doesn't matter because you know the mechanics of the problem here. I just picked one. I just picked that one because it seemed interesting to me in terms of figuring out the delta V magnitude, but I'm sure that in the notes that's not what we have. But that's not important because the process used what matters. Okay? Delta V. I'm going to do V2 minus V1, obviously. And for completeness, my delta V has to increase V1 all the way to V2 like that. Okay. What is V2? This is an elliptical orbit, so I better use this Viva equation. Mu 2 R over 1 over A like that. Now, is the point of application, and I'm talking about orbit number 2. Is it the apogee or the perigee of orbit number 2? Well, it turns out that this is the perigee of orbit number 2. I'm going to say RP2 because now I have 2 ellipses, so 2 perigees could be involved in the process in 2 apogees. So to make things super accurate, I'm going to say R perigee of orbit number 2 and semi-major axis of which one? Well, I'm talking about the green orbit, right? Just figuring out this term. So this is semi-major axis of orbit number 2, like that. Then minus the speed along the initial orbit, which is orbit number 1 at that point. So this is an ellipse. I'm going to use this Viva again, its most generic form. 2 over R minus 1 over A. Now at this point of application along orbit 1 was its apogee, right? Just look at the red ellipse. Its perigee was here, but that was the apogee. So I'm going to say R apogee of orbit number 1. And 1 over its semi-major axis, or in other words, semi-major axis of orbit number 1, like that. And that will give you a delta V, which is indeed positive. All right, so you see, you don't even need to go back to any of those equations because all you really need is a drawing, and all you need to know is the one equation, which is this Viva equation. It doesn't get any simpler than that, really. Okay? So we looked at cases where all we needed to change the initial orbit up to or down to the final desired orbit was one impulsive coplanar tangential maneuver. Okay? So single impulsive coplanar tangential maneuver was good enough to take us from where we were to where we want to be. But turns out that in other situations, that's not good enough because here the tangential assumption and the impulsive assumption meant that both orbits were intersecting at one point, right? You see this point being common to both the initial and the final orbit. So that was the implication of all of our assumptions. Yet, you may want to go from one circular to another circular orbit. You don't want to go into an elliptical orbit. So how could you go from one circle to another circle if both orbits don't intersect at any point? Because this is exactly what we have in that situation, right? 4.2 was called, yeah, right? So if you have one circular orbit around M1 and you want to go on to another circular orbit, which has to be centered at the same M1, obviously, well, you can't really do it in a single impulsive maneuver because those two orbits don't share a common point. So in that situation, the only way to do it is to apply two impulsive tangential coplanar maneuvers, okay? Meaning that the strategy as a heads up will be to go from here, 1 delta V, delta V1, to go from here into a higher elliptical orbit, like that. So spacecraft would follow this half elliptical orbit, which is known as a transfer orbit. And when it's going to reach this point, you'll have to apply another propulsive maneuver to increase the speed again, to go from here to the final orbit. Okay? So 1 delta V to go from circle 1 to transfer, and then another delta V to go from transfer to final orbit. Awesome. And that kind of maneuver is referred to as a double impulse maneuver for obvious reasons, right? Because the whole thing or the whole transfer cannot be completed with one maneuver, but then you need two of those maneuvers. So double impulsive maneuvers. And the first one we're going to look at is a maneuver known as Hohmann transfer. So Hohmann transfer is exactly what I've described with my little sketch here, is that you go from one circular up or down to another circular by a set of two impulsive maneuvers, okay? So let's analyze how it's going to work. We have the initial orbit, which is a circle in red. This, orbit 1. But that's not the circular orbit you want. What you really want is a bigger circular orbit. Like this. So two circles sharing the same center. That center is obviously the primary attracting body M1. Like that. So the trick is to, again, apply one delta V maneuver, that we're going to denote delta V1, to kick yourself onto what's known as an elliptical transfer orbit. So you go from circular to a bigger ellipse, and you stop the transfer here. So you only complete half of the elliptical transfer orbit. And at that point, you apply another delta V maneuver, delta V2, to then circularize the transfer orbit and end up on the orbit number 2, like that, okay? So how can we figure this thing out in terms of net delta V budget? Well, it's going to be pretty straightforward. So I'm going to do the work here for small circle to big circle, but obviously knowing how things are done, you could easily do the other situation, which would be a big initial circle down to a small final circle. But I'm going to let you do that situation on your own again, because this is so straightforward and easy that you can't really go wrong, assuming you draw it properly. So this is our vector that we're going to say RC1, and this is RC2, the radius of the second circular orbit. Okay, so the net delta V is going to be delta V1 plus delta V2. So all you have to do here to figure this is to apply what we saw twice. We calculate the delta V1 as a transfer between small circular up to a big elliptical orbit. This is your delta V1. And for delta V2, you would go from a small elliptical orbit up to a big circular orbit. Very straightforward. So let's do it for completeness, but obviously I trust that you could derive all this on your own. So delta V1, this guy. If this is V transfer, where the transfer orbit is highlighted in blue, and you had V1 like that, well, obviously Vt, so velocity of the transfer orbit, is larger than the velocity along the circular orbit, because the size of the transfer ellipse is larger than the size of the initial circle. So we're going to say Vt minus, I'm going to color code it as I did previously, so that there's no excuse to go wrong. V1 and Vt. Okay, so this is Vt minus V1. And there we go. So what is Vt equal to? This is an ellipse at its perigee, right? Because this is the closest point to M1. If you look at the blue elliptical orbit, so I'm going to apply vis viva mu times 2 over r minus 1 over a. R of which one? R of the transfer orbit at its perigee, minus 1 over the semi-major axis of which one? Well, the transfer orbit, which is t, like that. All this is for Vt. Now minus the speed we had along the initial circular orbit, so V1, which is simply vis viva applied to circular orbit, which is mu over r. R of what? R of the circular orbit, number 1. Good. And all this will give you delta V1 being a positive number. And then you need to figure out delta V2, because what you're asked is to perform the complete delta V budget, to go from orbit 1 to orbit 2, or in other words, calculate the net delta V, which is just the summation of delta V1 and delta V2. So delta V1, let's see what we have. Delta V2, sorry. So delta V2 is here. So we are kicking ourselves into a high energy orbit with V2 like this. And we were coming from an orbit that was elliptical, yet lower energy than the final orbit. So this is Vt in this direction like that. So delta V2, just by looking at this, is going to be V2, the final orbit, minus the speed we had along the transfer orbit. At what point? Well, now we are at the apogee of the transfer, so we're going to take that into account in a moment. So coming back here, so V2 is a circle, so square root of mu over r. At what point? Well, at this point, which happens to be RC2 in terms of distance, so RC2 minus V along the transfer orbit at its apogee, right? I'm always referring back to my diagram to make sure I don't mix things up, and I would highly recommend you do the same. So this is an elliptical orbit, so vis viva applied to an ellipse, 2 over r minus 1 over a. R, is it r perigee or r apogee? Well, we're now looking at maneuver number 2 here. So this is apogee, and I had used t and not nt. So this is radius along the transfer orbit at its apogee, RTA, minus 1 over a. Wait, am I looking at which orbit is that? Okay, let's go back. VT, transfer orbit, and therefore I need to use the semi-major axis of this transfer orbit, so A subscript T. And that will give you delta V2, which will be a positive number. So altogether, you could write that delta V total is square root of mu over 2 R TP minus 1 over A transfer minus mu RC1 square root of plus square root of mu RC2 and then minus the last speed expression here minus square root of mu 2 over R TA minus 1 over A of the transfer orbit. And altogether, that will obviously give you something positive because you did things in the right order. Okay? And again, don't necessarily look or try to compare that with what's in the lecture notes because I just picked an arbitrary solution where the initial was a small circular orbit and the final one was a large circular orbit, and maybe I've done the other way around in the lecture notes. I don't even know. Okay? It doesn't matter. One thing to realize here is that the semi-major axis of the transfer orbit will never be explicitly given to you. So it's going to be up to you to calculate it. So I'm going to say where semi-major axis of our transfer orbit. Well, that is easy because this is simply RC1, the radius of the initial orbit, plus RC2, the radius of the final orbit, divided by 2. And obviously, we're going to let you know what is the initial orbit we are into and what is the final desired orbit we want to go into. So you will have access to those two variables. So all you have to do is to sum them all up together and then divide by 2. Okay? Easy peasy. Easy peasy. We're just applying this viva over and over and over again. Just apply to different situations. And again, all we have to do is draw that little diagram with all the variables properly labeled with their direction as well and things like that, okay? And that specific maneuver that combines two burns is referred to as a Hohmann transfer. Okay. Now, another very similar situation is when you want to go from an elliptical orbit to another elliptical orbit, yet those two orbits do not share a common point. So in other words, the apogee and the perigee of an orbit does not match the apogee or the perigee of the other one. But the assumption here is that they share the same major axis line, okay? And that would be in 4.2.2. So that would be burn or transfer between elliptical orbits that share a common apse line. Okay, the apse line is, think of it as the line through which the major axis goes through. So, let's say that this is your initial elliptical orbit, and that is the final elliptical orbit. Let's figure out M1, and let's say this is the perigee and the apogee of the second one is over here, and that this is what we have, like this. Okay, So this is, say, orbit 1. And in green, we have the desired or final orbit number 2. Okay? So let's say we are traveling along orbit 1 and we say, oh, gee, I'm not in the right orbit. I need to go into a higher elliptical orbit. So what you do is that you kick yourself onto what you know now as being the elliptical transfer orbit, like that. Boom. And all you have to do is half an orbital period along this transfer orbit. Because if you keep coasting along the transfer orbit, you would come back to orbit 1 like that, okay? But that's not what you want. What you want at that point is to go from the small elliptical transfer orbit to the larger final elliptical orbit. So again, you need 2 burns. A first delta V at this point, and a second delta V at that point. Now, let's scale things properly. So orbit 1 is smaller than the transfer orbit. So I'm going to draw V1 like this. And the speed along the bigger transfer orbit compared to orbit 1 has to be larger. So I'm going to draw V2 like this. And here, let's say I have, or V transfer, sorry. V transfer at that point, another V transfer, but at this point. And then obviously because the largest of all these 3 orbits is orbit number 2, it's going to have the largest speed at that point. So V2 larger than VT. Now this is R1 at its perigee, whereas here is going to be denoted as R2 at its apogee, right? So delta V total is going to be delta V1 plus delta V2, where delta V1, I'm going to go faster because I'm assuming that you know how to do things properly. Now there are no circular orbits involved, so it's going to be 2 over R minus 1 over A, and this 2 times. But obviously those 2 terms aren't exactly equal because I kind of skipped a step. But delta V1 was Vt minus V1. So Vt is the transfer orbit in blue. So 2 over radius of the transfer orbit at its perigee. Okay, minus 1 over semi-major axis of the transfer orbit. All this is for Vt. V1 is the speed along the initial small elliptical orbits. I'm going to write 2 over R1 at its perigee minus 1 over semi-major axis of orbit number 1. Nice. And that is for delta V1. Boom. And obviously this guy is larger than 0 because you had your hand sketch diagram and you made sure that this was the largest speed and that the smallest and that first application of maneuver. And then delta V2 is going to be V2 minus the speed along the transfer orbit at that point. Those 2 are elliptical orbits. So this ellipse minus another ellipse. The speed along ellipse is vis viva, 2 over R minus 1 over A minus square root of mu times 2 over R minus 1 over A, like that. Now let's plug the subscripts appropriately to make sure that we don't just end up with 0, obviously, here, right? because as it is, this is equal to 0, but let's specify which radius are we talking about and which semi-major axis. So that term here is for velocity 2 at its apogee, so I'm going to write radius orbit 2 subscript A at its apogee minus 1 over semi-major axis of orbit number 2. And all this is for the transfer orbit at its apogee, so I'm going to say RT for transfer A for apogee minus 1 over A of transfer orbit, just like that, okay? So all this is for delta V2, and I'm not going to rewrite them in terms of delta V total, because all you have to do is to take this and do this plus that, and that'll give you your answer 100% on an exam, and that'll make me happy, and therefore that will make you happy, okay? So you help me, help you, essentially. Whew, good stuff, good stuff. I think I'm going to end here for this lecture, because that seems like a good point to stop. So that kind of covers the very fundamentals of orbital maneuvers, and specifically for impulsive, coplanar, tangential maneuvers. So in the next lecture or so, we're going to look at more complex maneuvers that will allow us to not only stretch or compress the orbit in terms of semi-major axis and eccentricity, but also change the orbital plane in 3 dimensions, changing radian, changing inclination. And also going to look at interplanetary travel, how to go from one planet to another planet, and carefully timing the delta V's to ensure that we don't miss a planet upon arrival. And also, what else? We want to talk about phasing maneuvers, which is like a docking, rendezvous and docking maneuver. So how to catch another spacecraft which is orbiting, say, ahead of us or behind of us. So that's going to be quite interesting, and that will be all next time. So as usual, I hope you enjoyed, and I'll see you soon. Goodbye.